Hi, welcome. Today in this video we are going to see basis and dimension part 2. We are going to see some general properties of finite dimensional vector space. General properties of finite dimensional vector space. Now the first property. Every linearly independent subset of finitely generated vector space V of f is either itself as a basis or it can be extended to form a basis. Or this theorem can also be stated as, let V of f be a finite dimensional vector space and S is equal to alpha 1 alpha 2 alpha m, a linearly independent subset, then prove that either S itself is a basis or it can be extended to form a basis. Now see here, what is V? V of f is finite dimensional. What is V? V of f is finite dimensional. What is S? S is linearly independent subset of V of f. Is it? Now what you have to prove? Either S itself is a basis or S can be extended to form a basis. S can be extended to form a basis means you are adding some elements of V to S and then you are saying it is a basis. Is it clear the statement? If S is a linearly independent subset of finitely generated vector space V of f, then either S is a basis or it can be extended to form a basis. I think the statement is clear. Okay, now we will see the proof. Now take. What is V of f given to you? V of f is a finite dimensional vector space, it is given. And it is also given S is equal to alpha 1 alpha 2 alpha m, linearly independent subset of V. Is it? It is linearly independent subset. Those two are given to you. Now what you have to prove? S is a basis or S can be extended to form a basis. S can be extended to form a basis means you will add some more elements from V to the elements of S and that you will call it as extended set of S. Okay. Now see here. Now given that V of f is a finite dimensional vector space. So its dimension is finite. Therefore, let us assume dimension of V is equal to n. What do you mean by dimension? Dimension is nothing but the number of elements in the basis set. So, dimension of V is equal to n you have taken. You can assume a set with n elements in V as its basis. Okay. Now, V is finite basis. Let B is equal to beta 1, beta 2, etc. Beta n is the basis of a vector space V. Okay. Now, what are alphas? Alpha 1, alpha 2, alpha m is independent, linearly independent subset of V. So, they are the elements of V. Because B is the basis set, every element of V can be expressed as a linear combination of basis elements. Is it? So, what will you say? Alpha 1 is the linear combination of betas and alpha 2 also linear combination of betas and alpha m is also linear combination of betas you can take. Okay. Now, take extended set of S as S1, that is you are adding the basis elements to the set S, that is alpha 1, alpha 2, alpha m, beta 1, beta 2, beta n you are taking and you are calling it as an extended set of S. Extended set of S, how it is obtained? For the elements of S, you are adding the basis elements of V and you are saying that set is the extended set of S. You are calling it as S1. Now, clearly L of S1 is equal to V. Clearly, L of S1 is equal to V. Now, each alphas can be expressed as a linear combination of betas. Is it? I told you, because alphas are the elements of V, B is the basis set. So, every element of V can be expressed as a linear combination of its basis elements. So, betas can be expressed as a linear combination. Therefore, S1 is linearly independent. Because why S1 is linearly independent? if you consider the set S1, alphas can be expressed as a linear combination of betas. So from in one set, one element is expressed as a linear combination of the other elements, means that set is linearly dependent. So what you are saying, S1 is linearly dependent. Since S1 is linearly dependent, by the known theorem, any element in S1 can be expressed as a linear combination of its preceding vectors. Okay, so this vector must be the vector which can be expressed as a linear combination of its preceding vectors must be from betas. It should not be from alphas, because alpha 1, alpha 2, alpha m is linearly independent set. Okay, so take one beta I. So from S1, you have taken from S1 is this. From S1, out of betas, take one beta I, and that beta I is the linear combination of its preceding vectors. Okay. Now, what you are doing is eliminate beta I from S1. If you eliminate beta I from S1, you will get S2 like this. That is alpha 1, alpha 2, alpha m, beta 1, beta 2, beta I minus 1. You are eliminating beta I, and beta I plus 1 and so on, beta n. This is it. Now, this is the set S2 is obtained from S1 by eliminating one element. Okay. So, clearly L of S2 is equal to V. This you have seen in the previous video, how it is. Clearly L of S2 is equal to V. Now, S2 is linearly independent, then S2 will be the basis. That means S2 is the extended set of S. Is it? If S2 is not linearly independent, it will be linearly dependent. Then if S2 is linearly dependent, again you will repeat the process. Again there exists one beta out of n minus 1 betas that can be expressed as a linear combination of its preceding vectors. Again you will eliminate that beta which is expressed as a linear combination of its preceding vectors. You will get another set S3 with the elements. From S you are eliminating two elements. So S3 you will get. If S3 is linearly independent, it will be the basis having some betas. If not, it is linearly independent, then S3 will be linearly dependent. You will continue the process until all the betas are exhausted. Therefore, either S is, you will remain with S and it is the spanning set of V. Therefore, either S is a basis or S can be extended to form a basis. Is it clear? This set will be a basis of V and will contain S. Every linearly independent subset of finitely generated vector space is either a basis or can be extended to form a basis. I think it is clear. What is the concept we have used in this problem? You have taken S as a linearly independent set, and given that V of f is a finite dimensional vector space, since it is a finite dimensional vector space, it has a basis with some finite number n elements. Since every element in V can be expressed as a linear combination of its basis elements, you can take the extended set by adding the set of elements, basis elements to the set S. You got the extended set, and from that extended set, if it is linearly independent, it will be basis, because that extended set, linear span of that extended set is becoming V. Okay. Now, if it is not linearly independent, it will be linearly dependent. If it is the linearly dependent, by known theorem, there exists one vector which can be expressed as a linear combination of its preceding vectors. Okay. So, the vector which has been written as a linear combination of its preceding vectors will be eliminated from that set, and you will get the new set. If that the linear span of that new set will be equal to V, and if that set is linearly independent, it will be the basis, being an extended set of S. Otherwise, you will repeat the process until all the betas can be exhausted. You will remain with the linearly independent set. That set will be the basis. Okay. So, what can you say? Every linearly independent subset of a finite dimensional vector space can be a basis or it can be extended to form a basis. That is the theorem. Okay. Now this is one of the important theorem. See the next one. Let S is equal to alpha 1, alpha 2, alpha n be the basis set of a finite dimensional vector space V of f. Then prove that for every alpha belongs to V, there exists a unique set of scalars a1, a2, an belongs to f such that alpha is equal to a1 alpha 1 plus a2 alpha 2 plus so on plus an alpha n. Now what is S? S is the basis set. Basis set means S is equal to what is given to you? Alpha 1, alpha 2, alpha 3 and so on alpha n. This is S. How is it? It is basis of V. Since it is the basis of V, L of S is equal to V. That means any element alpha belongs to V will be the linear combination of elements of S. Alpha will be the linear combination of elements of S. Like this, alpha is equal to a1 alpha 1 plus a2 alpha 2 plus so on an alpha n, where a1 a2 an belongs to F. Now what is your aim is these a1 a2 an are unique. Okay, that we have to prove. In order to prove that, now take S as a basis set of finite dimensional vector space and take a1 a2 an belongs to F such that alpha is equal to a1 alpha 1 plus a2 alpha 2 plus so on an alpha n. Since S is the basis of finite dimensional vector space, V of F implies L of S is equal to V. Now if possible, let there exist another set of scalars b1, b2, bn belongs to F such that alpha is equal to b1 alpha 1 plus b2 alpha 2 plus so on bn alpha n. Now alpha being equal to a1 alpha 1 plus a2 alpha 2 plus so on an alpha n, and it is also equal to this. So from these two you can write a1 alpha 1 plus a2 alpha 2 plus so on an alpha n will be equal to b1 alpha 1 plus b2 plus alpha 2 plus so on bn alpha. Bring all the elements to one side and take common. So you can arrange this equality like this: a1 b minus b1 into alpha 1, a2 minus b2 into alpha 2 plus so on an minus bn into alpha n is equal to 0. What are alpha 1, alpha 2, alpha n? They are the elements of the set S. What is S? S is basis. When will be the set is said to be basis? If it is linearly independent and L of S is equal to V. Since S is linearly independent, the linear combination of the elements of S is equal to 0 implies the constants existing in that linear combination should be 0. So a1 minus b1 is equal to 0, a2 minus b2 is equal to 0 and so on an minus bn is equal to 0. That implies a1 is equal to b1, a2 is equal to b2 and so on an is equal to bn. Okay. So for every alpha belongs to V, there exists unique set of scalars such that a1 a2 an belongs to F. Alpha is equal to a1 alpha 1 plus a2 alpha 2 plus so on an alpha n. If V is a finite dimensional vector space, then any element in V can be expressed as a linear combination of its basis set of elements uniquely. That means the coefficients existing in the linear combination should be same. Okay. Now see that next property. That is, every set of n plus 1 or more vectors in an n-dimensional vector space is linearly dependent. What is this? Now see here, V of F is the n-dimensional. V of F is n-dimensional. That means dimension of V of F is equal to n. It is given to you. Now what you are going to say? Any set which is having n plus 1 or more elements. Suppose S is equal to alpha 1, alpha 2 so on, alpha n plus 1 or more will be linearly dependent. Okay. Now see how you are going to conclude it. Now let V of f be a vector space with dimension V is equal to n. Sn is equal to alpha 1, alpha 2, alpha n plus 1. It is a subset of V and it is having how many elements? N plus 1 elements. Now what you have to say? S is linearly dependent. If it is not linearly dependent, it will be linearly independent. If it is linearly independent, now what's the previous theorem you have proved? Any linearly independent subset of a finite dimensional vector space F, V of f, can be extended to form a basis or itself is a basis. So suppose S is linearly independent, itself will be a basis or it can be extended to form a basis. That means S is having either n plus 1 elements or more elements. It is the basis. So the number of elements in the basis set is said to be the dimension of the vector space. So S is having more elements, n plus 1 elements are more and it is becoming basis. So the dimension of basis will be n plus 1. But you know that any basis set will have the same number of elements. That will be the number of elements in the basis set will be the dimension. So the dimension of a vector space is invariant. So it won't be once n and other time it won't be more than n. Is it? So since the dimension of vector space is invariant, that is the number of elements in any basis set is same, it is a contradiction. Contradiction to what? Suppose if you take S with n plus 1 elements is linearly independent, you are getting the contradiction. Therefore, every set which is having more than n plus 1 or more than n plus 1 vectors will be linearly dependent in a vector space of dimension n. Now is it clear? See, it is a contradiction to every basis of V which contains exactly n vectors, because dimension of V is equal to n, every basis must have the same number of elements according to invariance theorem. So this is due to, or suppose this is linearly independent. If you take, you are getting the contradiction. So any set which is having n plus 1 or more elements in a finite dimensional vector space of n will be linearly dependent. Okay. Now see the next property. What is the next one? Let V of f be finite dimensional vector space of dimension n. S be a set of n vectors of V such that L of s is equal to V. Then S is basis of V of f. See here. Now what is given? V of f is finite dimensional and dimension is V. N. Dimension of V of f is given. It is equal to n. Okay. Now let S be a set of n vectors. How is S? S is having n vectors, alpha 1, alpha 2, alpha 3 and so on, alpha n. S is having n vectors. Now, and how is S? L of S is equal to V. Now you have to say that S is a basis. Now in order to say that S is a basis, if S is linearly independent, your problem is over. Okay. Now see how we are going to say. Let V of f be a finite dimensional vector space. S is equal to alpha 1, alpha 2, alpha n. Be a subset of V such that L of S is equal to V. Now we prove that S is a basis of V. In order to say that S is a basis of V, if S is linearly independent, then S will form a basis, because the two conditions for the definition of basis is satisfying. When will you say any set is a basis that is linearly independent? L of S is equal to V. L of S is equal to V is given to you. If S is linearly independent, automatically it will be the basis. If S is not linearly independent, it will be linearly dependent. Since it is linearly dependent, there exists a proper subset of S forming a basis of V. Is it? Because you will eliminate, why? We get a basis of V containing less than n elements. That means, see, S is linearly independent means you will write one vector in S as a linear combination of its preceding vectors, and you will eliminate that vector which has been written as a linear combination of its vectors. Then you will get the subset of S. If it is linearly independent, it will be a basis. You have seen in other problems, other properties. So you will get a basis of V containing less than n elements if S is linearly independent. But the basis is a dimension of V of S is n. Any basis should contain n elements. So if S is linearly dependent, you are getting a contradiction. Therefore, S must be linearly independent. Therefore, S is a basis. This is another property. Okay. Now see the next one. Let V is a vector space which is spanned by a finite set of vectors beta 1, beta 2, beta n. Then prove that any independent set of vectors in V is finite and contains not more than n elements. Okay. Now see, what is given to you? V is a vector space which is spanned by a finite set of vectors n. That means, now suppose S is equal to beta 1, beta 2, beta n, you are having L of S is equal to V. So L of S is equal to V implies V has finite basis. Is it or not? V has a finite basis. When will you say that any vector space is finite? Any vector space is said to be finite if there exists a subset which is having a finite number of elements such that L of S is equal to V. So L of S is equal to V and S is having finite number of elements, then V has a finite basis and dimension of V should be less than or equal to n. Every subset S of V which contains not more than n vectors is linearly dependent. Okay. Now the set which is having less than n elements will be linearly dependent. That only you have to prove, is it? Now any independent set of vectors in V is finite and contains not more than n elements. Now you are saying in the other way, the set which is having more than n vectors will be linearly dependent. Okay. Now see the next property. This is about the dimension of a subspace. Suppose V of F is a vector space and W is a subset of that vector space. Suppose the dimension of vector space V of F is finite and it is equal to n, then any subspace dimension will be less than or equal to n. That is the property here. Let V of F be a finite dimensional vector space of dimension n and W be subspace of V, then prove that W is a finite dimensional vector space with dimension W less than or equal to n. What is given to you? V of F is finite dimensional vector space and you have assumed that dimension of V is equal to n. Now let W be the subspace of V. Now what you have to prove? Dimension of W is less than or equal to n. This you have to prove. In order to prove that, see here, dimension of V is equal to n given to you. Since dimension of V is equal to n, according to the property, every n plus 1 or more vectors, every set which is having n plus 1 or more vectors of V is linearly dependent because dimension of V is n. Okay. Now W is a subspace of V. It follows from V, each set which is having n plus 1 vectors or more in W will be linearly dependent. Okay. That is, any linearly independent set of vectors in W can contain at most n vectors, because if n plus 1 vectors is there in that set is becoming linearly dependent. So S is equal to alpha 1, alpha 2, alpha m be the largest linearly independent subset of W. Therefore, you can say that this S is linearly independent and L of S is equal to W means L of S is equal to W means that will be the basis. Okay. Now clearly L of S is proper subset of W, is it? Now let beta belongs to W and S1 is equal to alpha 1 alpha 2 alpha m beta. The largest linearly independent subset of W contains m vectors, is it? So it is having more than m vectors. Therefore, it is linearly dependent. S1 is how? It is linearly dependent. Since S1 is linearly dependent and alpha 1, alpha 2, alpha m are linearly independent, beta can be expressed as a linear combination of elements of alpha 1, alpha 2, alpha m. That implies beta belongs to L of S. Therefore, you have taken beta in W and you are able to show that it is in L of S. So, W is subset of L of S. Already you said L of S is subset of W. Therefore, L of S is equal to W. S is a basis of W. W is finite dimensional vector space with the dimension of W less than or equal to 1. Here, note, if V is equal to W, the if and only if dimension of V is equal to dimension of W. Now, see this one. Let V of F be a finite dimensional vector space of dimension n. Then prove that any set of n linearly independent vectors in V form a basis of V. It is sure. Now, given that V of F be a finite dimensional vector space and dimension of V is equal to n, let S is equal to alpha 1, alpha 2, alpha n be linearly independent set of n vectors. Now what you have to prove? S is a basis of V. Suppose that S is not a basis of V, S is linearly independent, therefore S can be extended to form a basis. That means the basis set is having more than n elements, which is a contradiction because dimension of V is equal to n. Therefore, it should be the basis. L of S should be equal to V. Therefore, S is a basis of V. See here. Now, using this theorem, if the number of elements in a given set is equal to the dimension of the vector space, then if you want to say that set is a basis, it is enough if you show that it is linearly independent. Okay. Now, these are the properties of vector space. With this, I am stopping. Thank you.